Hi everyone, welcome back to part 2 of this Using Statistics classwork. We're continuing on with the discrimination or random chance lab portion now that people have had a chance to contribute their data to our spreadsheet. We'll be picking up with number 6D and we'll need to go back to our Google spreadsheet with our class data here. So as a reminder of how to get there, in each of the classworks there's a link to that spreadsheet, that Google sheet right at the top. So here we have our classes data. Okay, so let's take a moment and walk through the different worksheets we have here to try to understand them a little better. You may have noticed there are different tabs that look different in here. So let's talk through what each of these are. So this first sheet is where we entered the data for all of our simulated samples. And it was set up so that it automatically calculated the mean for each one of those simulated samples. Okay, so hopefully you had a chance to go through and do this simulation and put your 10 samples, your 10 simulated samples in there and see that it calculates, the mean for you. Okay, so here's all the data that we collected. And the next sheet we can see is called copy of all means, no rounding. This is if we just took that first column of sample means, right? So I'm talking about this first column of sample means. If we took this is just saying grab this information and put it here in this first column, right? C starts with 48 and we get down 45, 38, 39. See, this one starts with 48 and we get down 45, 38, 39. So it's just grabbing that info and moving it here. It's hiding all the in-between sample values, right? So then here we have for every person's second sample, the mean that they got, third sample means, fourth sample means, and so on. Okay, so this still looks kind of messy. It's hard to look at these places where it has this hashtag div over 0. That's just showing us this is data for a person who hasn't, or this student hasn't had a chance to put their data in, and so it's just throwing up an error showing that that information is blank, right? So it's a little hard to look at like this. So this next tab over is, again, here we see everything. Then if we hide these samples of data and we just look at the means, here we are. And then this next page, it's doing the same thing. We're looking at those same columns, those same sample means, but just making it look a little nicer on the eyes by rounding each of these numbers to the nearest value, right? So like at the top here, these would be rounded 48, 38, and 48. And so it's just a lot easier to see kind of this way. It's easier on the eyes. And then we can clearly see, oh, these ones that look weird, those are just the missing data people. Okay, so again, it's just kind of organizing our data for us. And this last tab that's labeled SDOM, and we'll talk about that a bit later, what that stands for and what it means. So if we click here, we see what looks like a graph, right? And so here we can see the number line for this graph or figure goes from 26 up to 64 or higher. Okay. And then what this is doing is it's counting, it's saying, okay, here, how many of these sample means were 28 or 29? None of them. None of them came out as those numbers. Okay, how about 30 or 31? In all of these values, we should have one 30 or 31, right? And so it's just counting. It's looking and counting. There are 2 means that were 32 or 33, 2 that were 34, or sorry, 5 that were 34 or 35, right? So it's just showing us in the column first how many means from all of these sample means that we've put together, how many were these values, right? So we can see some of them 46 or 47. There were 22 that were a 46 or 47. And then the circles to the right, the dots in our dot plot, are just representing that value visually. So we can see 1, 2, 5, 4, 22, 12, and so on. So this gives us an idea of, the quantity. We can see the ones that stick out really far are the ones that have really high numbers. So it gives us an idea of the overall shape of our distribution. And then at the bottom it also tells us how many of those simulated samples we ended up with. So back to number 6D. Display the distribution. We will pool your results with the rest of the class and display the distribution of average ages visually, as we just saw. And then after we take a look at it and really think about it, I'm going to have you roughly sketch what that distribution looks like. Okay. So remember that a distribution is just a way of listing or showing all of our data values, like we have here, and how often they occur. So in our case, we're looking at this distribution of average ages from our repeated simulation of randomly firing 3 employees. Right? So these circles and these numbers that we see, we're not looking at, they don't represent all of the ages that were randomly picked, but rather if we randomly pick 3 people to fire, what is the average age of the group who were fired? So each of these values, each of these circles or dots that we see in our distribution represents a group of 3 employees, right? It represents one of those simulated samples. So we can see here from 26 to 64, we can kind of see the shape here, right? And we're going to do a little sketch of what the distribution looks like. So I realize that it can be really hard to draw on a virtual document, and I very recently have lost my pen stylus that I usually use to do that on my computer. So I went ahead and I did a hand sketch on a notebook. Okay. So I recommend keeping a notebook where you can sketch and draw things out. We're going to do that a lot in this class. And so here I'll make a note. This is corresponding to classwork 2, part 2, 6D. So here's my sketch. And you can see that I messed up. It's not perfect. It's really, really rough. And you can be as detailed as you like here. If you want it to be a very detailed, precise drawing, go for it. If you're okay with just something quick and dirty like me, then just remember these notes are for you, right? So you'll be the one looking back on them. So go ahead and take the time however you want to do your rough sketch. And then I also, right, so here's my comparison. And then I also just wanted to demonstrate a more common layout for this type of graph while we're here. So to do that, I'm going to take a little screenshot of our distribution of our dot plot. And then I'm going to paste it into a blank document just so that I can then rotate this so you can see what that graph looks like if we were to tilt it on its side. Right, so it's the same graph as this, but instead of being presented with the number line vertically where our our dots are out to the right. The more common way that we tend to see dot plots displayed is like this, where we have a number line along the bottom and we see the stack of dots up above the numbers. Right? So you may want to think about it in this way, since this is more common. It's just harder to get displayed in something like Google Sheets. Okay, so let's see here. Let's go back. Oops, there we go. So here we are to 6E, right? So go ahead, take a moment, do your sketching, however you do that, and then come back for 6E. And on 6E, we're going to estimate the probability. So to do this, we're going to count the number of times our class computed an average age of 58 years or greater. So this involves looking back at our spreadsheet, and probably the easiest way to do this is to look at the spreadsheet with our dot plot. So we could go back further, and as you see on these mean summary tables, all of the ones that were 58 or higher, so for example, 58 or I thought there were some 58.33, right? So 58 or higher, it flags it as red. So we could figure out how many, we know how many total we have of samples, and then we count, well, how many of those were 58 or higher? 1, 2, 3, 4, 5, and 6, right? But we can also see it pretty easily here on our dot plot. So click back over to the Google Sheet, this tab at the bottom that says SDOM. And again, I'll explain what that stands for in a minute. So now here we can see the frequencies and the total very clearly. And keep in mind that this very probably could be different numbers than you see in this class spreadsheet than what I'm showing here, because it is a live document. It's a living document that gets updated for each individual class and each individual's data. So as of right now, when I'm recording this, I can see that for this class, there were 6 samples with a mean of 58 or higher out of a total of 180 samples. So we can see that here in row 19, where we're looking at means of 58 or 59, and column C, frequency or how many, that's where we can see and read this as saying that there were 6 samples with a mean of 58 or 59. We can see nothing was higher than that. So here we had 6 samples with a mean of 58 or greater. And again, yours may be different from 6, and that's okay. Go ahead and write down whatever you see on your end. So go ahead and note down the number you see in the spreadsheet on 6E of the classwork. The number of times our class computed an average age of 58 years or greater is, and in my case, that's 6. Now, the next part of this asks us to estimate the probability that, simply by chance, the average age of the 3 chosen to be to be fired would be 58 or greater. Okay. Well, we have all this wonderful simulated data right here. It's saying, okay, that's how many samples we got. Estimate. What do you think the probabilities are of this occurring simply by chance. Okay, so looking at all of this wonderful simulated data, as I said, representing all of these hypothetical samples, instead of just guessing, let's use these data that we generated to help us make a better, more informed estimate. So we know that it occurred, this 58 or greater average for a sample, about, let's see, so 6 times out of a total of 180 simulations. So that's not a super nice, easy round number to imagine in your head, like 6 out of 100. 6 out of 180 is a little harder. So let's go ahead and calculate and find out what proportion this is. So I'm going to take my calculator and I want to know, okay, we had 6 samples, average age 58 or greater, out of a total divided by a total of 180 samples in all. And I get a proportion of 0.0333. So I always find it easier to think about probabilities and proportions as a percent. So if we multiply this by 100%, since 100% is one whole, it may help to think of it as 3.33%, or a little under 3.5%. Okay, so I'm going to, for this part where I'm estimating the probability, it looks like that's about, and again, here be as detailed as will be helpful for you. So for me, I'm just going to make a very quick note because I already know this stuff. So I'm going to say about, we'll leave it without rounding it, but in my head, I'm imagining like about 3.5%. Okay. So in the end, when we did this simulation over and over and over, at the end, only about 3.5% ended up looking like what really happened at Westvaco. Right, so I would estimate this probably at about 3.5%. You can keep it close to the number. You can estimate slightly differently, but that's a good place to start. All right, so go ahead and make a note of what you get on 6E as well. Now for this next part, 6F, it asks us to interpret our result. So what do we conclude from our class's estimate in step E, that probability, whatever that happened to be on your end? About probably somewhere around 3.5 to 4%. Okay. So to interpret these results, remember why we did this whole simulation in the first place. So there's a company, Westvaco, and they fired 3 employees from a department during layoffs. The average age of the 3 people who were fired from the department was 58. Right? We have this from earlier on in this classwork. So versus the average age of the people that were kept on was 41.4. Now Martin sued, claiming that he was discriminated against because of his age, and that was why he was let go. Westvaco said it had nothing to do with age, and 3 people were simply chosen at random to be fired. So while it makes sense that this could happen, that they could have chosen 3 people at random and have it be 3 of the oldest workers, but the question really is, how likely is that to happen? Like, it can happen, but how often? How likely is that? Is it super, super rare, or is it like reasonable? Okay, because if it's super, super rare, then that doesn't look so good for the company. But if it's like reasonable, like, yeah, I could see how you could get 58, then, then it's not good evidence of discrimination. Okay, so we have discovered that around, we ran this scenario over and over, and noted the data each time that we got it, right, in our spreadsheet. And then we can see out of all those times that we did it, we can reasonably expect to see an outcome like Westvico's about 3.5, maybe 4% of the time, right? So if we're doing this totally at random, which is what we did to get this simulated data, it happens about 3.5, 4% of the time. Okay, so now the question is, okay, is that likely or unlikely? And this is where a lot of the interpretation comes in, right? So, where is the line that separates what we consider to be likely versus unlikely? And really, this sort of changes a lot from person to person or in different situations, right? So, for example, if I told you there's a 10% chance of rain tomorrow, would you be likely to take an umbrella with you? You know, is the risk sort of the likelihood worth the extra effort in that case? Versus what if I told you there was a 10% chance that if you went down to your corner store and got a lottery ticket, you'll win $1 million or more, right? 10%, is that worth that effort going to the store to get the ticket and getting a million or more? Right. So those likelihoods are all sort of relative to the situation. It's up to us as researchers and statisticians to take the evidence that we get, the values, the numbers we get. The number itself is not the answer. The answer is, okay, so then based on these values, what conclusions would we draw? You know, how would we interpret this? What does that tell us about how likely it is that something happened? Okay. So in this case, there's about a, I'm going to round up here, there's about a 4% likelihood of getting a sample with average age of 58 or higher if those people were chosen simply at random. Okay. So we can also think about it another way. Westvico says, hey, we did it at random and this is what happened. You know, that's the answer. We did it at random and this is what happened. Now, if the thing that happens about 4% of the time, right, as we can see happened here in our simulation, happened about 4% of the time, that means it does happen, right? Theoretically, it could have been one of those 4 times, happens about 4 in every 100 times. It could happen, right? So, how do we know that this just wasn't one of those times? It is random after all, and the stakes are pretty high here, right? If the company is found responsible, then they'll likely owe a lot of money to the plaintiffs and the other fired employees. So I want you to think about this like, you know, a real life scenario. Imagine you're sitting on a civil case, you're on a jury, and you're trying to weigh up the evidence in this case, right? So you find out we ran 180 simulations, and only 4% of the time did they look like what actually happened at the company. Okay? So, back to our classwork here, interpret your results. So 4%, 3.5, 4%. Is that number low enough that you think, nope, 4% is too low and I don't believe that's what happened based on this evidence? And if it wasn't random, then it makes them look guilty of age discrimination. Or do you feel that 4%, I mean, 4% isn't nothing. It's not it's 4 out of 100. Do you feel that 4% is high enough that there's some reasonable doubt there about what happened? Do you think it could, reasonably could it be at random? You know? So interpret this result that you got and indicate what you personally would think in terms of our court case. You should also note that whenever I ask you to interpret something, as I have here, really what I mean is explain it to me in words what this result tells us about this problem that we're discussing, right? The whole sort of situation. And on test one, I'll have at least one question asking you to interpret some result in the context of the question, right? So this might be a good question to hop over onto the class discussion board and discuss with other people if you're unsure about it. And then come on back for number 7 once you've had a chance to note your thoughts. So, number 7, what is the distribution from step D in the simulation? So, we're talking about this distribution. What is this called? And how is that distribution important? Well, we're talking again about this one, this SDOM here. Okay, let me just put these side by side. So we're talking about that SDOM or SDOM. The SDOM stands for Sampling Distribution of Means. Let me go ahead and make this bigger. Right, so the SDOM, it's just shorthand for sampling distribution of means. And you may think, okay, great, but what's the sampling distribution of means? So basically, sampling, that's what we did with our simulation. It's taking sample after sample after sample, or in this case, we simulated sample after sample, right? So we simulated that sampling process of getting one sample, getting another sample, and doing it repeatedly. And then we use that to generate some hypothetical data representing a lot of different samples, right? All the kind of possibilities we would see. Then, for each hypothetical sample, we calculated the mean of those 3 values in the sample. So we have all those means, and once we have those means, this graph gets updated to display each of those sample means. So this is a distribution of those sample means that we had. Or to say it another way, this is a sampling distribution, lots of samples, showing us the means for those samples. So sampling distribution of means. Now, this turns out to be a major tool in statistics, and it's one that we'll spend a lot of time focusing on later in the semester. So you will hear and see SDOM, sampling distribution, many, many times in this class. So we're going to repeat it over and over because it's a hard concept. So the sooner you start to understand this funky concept, then the easier other concepts will be to understand. So for now, as it asks, how or why is this important? So for now, let's just say this distribution was important in this problem because it let us quickly visualize and estimate, the chances of a certain scenario happening at random. Right? That's how we used it in this case. So once we have all these means, we can see, oh, these are the ones like our case, and these are the ones not. Okay, then, how can we use that then as information or evidence to make a decision? Now, on number 8, I clue you into a little fact. So in a typical court case, a probability of 0.025 or less is considered, sorry, I'm trying to get this zoom right here. It's very sensitive. Okay, so a probability of 0.025 or less is considered unlikely. Okay. And if we think about this 0.025, like I said, it helps me to think about it as a percent. So if we were to convert this, move our decimal 2 places to the right or multiply by 100, we can see that this is about 2.5%. Okay, so in a typical court case, a probability of 2.5% or less is considered unlikely. And if it's unlikely to have turned out with this, like this, with a fair process, such as random chance, then the court will consider this evidence of discrimination, right? If it's 2.5% or less, that means it's unlikely. So this is the legal definition of too unlikely. So in other words, the probability of the scenario occurring by chance is 2.5% or lower. That's considered too unlikely and can be considered as showing discrimination, right? So that's our cutoff point, 2.5%. If it's lower, unlikely, we say discrimination. If it's higher than 2.5%, we say, that's not unlikely enough, right? So no, it could have happened at chance. So again, we want to consider this. Are we able to then consider our result as evidence of discrimination? We want to think about it against that 2.5% benchmark in this case. Okay, so 8A, did the layoffs of workers in this department meet the court requirement? Okay, so I found a probability of about, I'm just going to round, about 3.5%. And this is above the cutoff that we discussed of 2.5%, right? The legal cutoff. So if it was below 2.5%, it could be used as evidence of discrimination. In this case, right, in our case, the court would not accept our simulated data as evidence of discrimination. Right, so our evidence would be out in this case, based on our actual data that we came up with. Okay. Now on B and C, you'll see there's a small blank on those. Here you're just going to fill in that probability that we got back on 6E. So here again, I'm just rounding. I know mine was about 0.035. Okay. So for B, so if our simulation had shown that the probability in the Martin case had been 0.01 instead of 0.035, what would the court's ruling be? Right, so we can, again, convert this to a percent. I find easier. We could move this 2 decimal places to the right, or we can multiply by 100, and we'd see that this 0.01 is equivalent to 1%. Okay, so we can see that 1%, how does that compare to our cutoff of 2.5%, right? 0.01 versus 0.025. Is it below our cutoff? Yes, it is, right? 1% is definitely lower than 2.5%. So in this case, yes, 1% would count as evidence of discrimination. Now, again, we're just practicing our decimals here. So if our simulation had shown that the probability in the Martin case had been 0.1 instead of 0.035, what would the court's ruling be? Well, here, 0.1, if we moved that decimal 2 places to the right, we would have to imagine that invisible 0 there, right? So 0.1 is actually the same as 10%. Right? Is 10% below our cutoff of 2.5%? No. So in this case, it would not count as evidence of discrimination. Okay. So take a look at B and C, and we can see the importance of decimal places and zeros. These are very important in this class. So 0.01 and 0.1, they look very similar, right? And in lots of situations, those numbers are very close. But in this case, we would interpret them in opposite ways, right? That 0 is really important. We can't just ignore it. So you may want to just do a little review of decimals and how that relates to percents and probabilities, because this is something we're going to be working with all semester. And I know lots of people have trouble in that area. Okay. So finally, let's tie this classwork back to our guided notes with number 9. So how did we use descriptive statistics and inferential statistics as tools to help us draw a conclusion about whether we suspect discrimination? So remember, descriptive statistics simply they describe a sample. So we really used one very important descriptive statistic, the mean, many, many times in this situation, right? We use that tool over and over and over. For each simulated sample, we considered the descriptive statistic of the mean for that sample. We were then able to look at lots of different sample means, evaluating what could happen in lots of samples, considering the patterns that we see, and then drawing a conclusion about what the evidence suggests. That part is using the tool of inferential statistics, right? Looking at these many, many samples and drawing a conclusion about kind of the bigger situation, right? Going from the sample to the kind of the population, that idea. That's where inferential statistics happens in this problem. So again, number 9 might be another good one to discuss further in the discussion board. And remember to save what you've added to this file, as you'll be submitting it on our assignment page to receive credit for completing part 2 of this classwork. So hope that helps.